Okay, picture this. You've got two pieces of rock pulled from 10,000 feet underground. To the naked eye, they are absolutely 100% identical. Same sandstone, same grains, same porosity. But here's the catch. One is completely saturated with salt water, making it entirely worthless. The other, full of oil and worth millions. You obviously can't tell them apart just by looking at them, and you certainly can't haul the entire reservoir up to the surface to check. So how exactly do you solve the mystery of invisible oil?
Welcome back to The Explainer. Today, we're diving into a really fascinating cheat sheet, the Batch 6 formula and key figure quick reference. We're going to use this to decode the extreme physics of downhole drilling. Together, we'll see exactly how complex math and incredibly high-stakes physics actually translate into crystal clear, actionable knowledge out in the field.
Here is our game plan for today. We're going to master 5 distinct engineering missions: finding oil with electricity, sealing rough boreholes, managing live well entry and pressure, freeing stuck pipe, and finally, overcoming massive friction in tight spaces.
All right, let's jump right into Section 1, finding oil with electricity.
So let's go back to our opening riddle and see how electromagnetism actually solves it. If you know how a standard electrical transformer works, you already understand the induction principle. We drop a tool down the wellbore equipped with a transmitter coil carrying an alternating current. That current generates a magnetic field, which then induces circular eddy currents in the surrounding rock. In pure engineering terms, the rock formation itself is acting as the secondary winding of a transformer. Those eddy currents then create their own magnetic field, which our receiver coil picks up. It's essentially a highly sophisticated metal detector, but instead of finding loose change, it's scanning the rock itself.
And boom, here is the punchline to that opening mystery. The reason we can tell those two identical rocks apart comes down to one stark electrical contrast. Salt water is packed with dissolved ions, right? So it conducts electricity incredibly well. Hydrocarbons, on the other hand, like oil and gas, are natural insulators. So a porous rock full of salt water reads as highly conductive, while the exact same rock full of oil reads as highly resistive. That one single contrast is literally what turns total guesswork into a multi-million-dollar discovery.
Now you might be wondering, how do we take those raw resistivity readings and turn them into cold, hard facts? Enter Archie's equation. You don't need to memorize the math right now, but you definitely need to understand its power. By plugging in the formation's true resistivity and its porosity, this equation calculates the exact fraction of the pore space that holds water. And by default, whatever isn't water is your hydrocarbon. This equation is absolutely crucial because it bridges the gap between raw electrical data and actionable reservoir knowledge. But the absolute best practical advantage of the induction log, nothing actually touches anything. Because it uses magnetic fields to induce currents, it requires zero electrical contact with the formation. This is a massive game changer. It means you can run this tool in oil-based or non-conductive drilling muds where traditional electrode tools would just be completely blinded. Moving right along to Section 2, conquering the rough borehole.
Okay, so we found our invisible fluids. Awesome. But now we're facing a physical nightmare. How on earth do you seal a wellbore when the rock wall isn't some perfect steel cylinder, but a rough, washed-out, totally irregular cavern? You use an inflatable packer. Unlike a rigid rubber seal, this tool has a reinforced bladder that you pump fluid into, allowing it to expand to more than twice its original running diameter. Think of it exactly like a blood pressure cuff. It doesn't just expand, it continuously conforms to whatever irregular, oval, or jagged shape the rock wall throws at it, maintaining a perfect seal even as the hole flexes.
But, and this is a very big but, you have to know your numbers. The absolute crucial takeaway here is that inflation pressure and differential rating are two completely separate things. Inflation pressure is what you pump inside the element to set the tool. Differential rating is how much well pressure the set tool can actually hold back. People conflate these constantly. If you pump too much inflation pressure trying to reach a washed-out wall, you will literally burst the bladder. And if it bursts, it might not deflate, meaning your routine test just turned into a very expensive, very frustrating fishing job.
While we're on the topic of permanent pressure containment, let's briefly touch on liner integrity. When you're running a liner string, the unbreakable rule of thumb is that the liner top must overlap the previous casing shoe by 300 to 500 feet. That specific overlap is heavily cemented and pressure tested because that joint isn't just structural, it acts as a non-negotiable permanent pressure barrier for the entire productive life of the well.
All right, Section 3, live well entry and pressure.
Things are about to get really tense.
Our third mission is live well entry, which is the incredibly high-stakes process of pushing tools into a pressurized live well without killing the well's flow first. If you're doing wireline work here, you use a lubricator, which is essentially a giant pressure lock. The sequence is absolute law. First, load the tool string. Second, pressure test the assembly. Third, equalize the pressure with the well bore. And only then, step 4, do you actually open the valve to the well. And remember, the lubricator must be long enough to swallow the entire tool string. Why? Because the golden rule that keeps everyone alive is this: never, under any circumstances, have two barriers open at the exact same time.
Now, what if you're pushing a rigid pipe, like coiled tubing, into that live well? Well, the well pushes back. We call this snubbing force. The math here is beautifully brutal. Force simply equals the well pressure multiplied by the cross-sectional area of the pipe. So if you've got 5,000 pounds of pressure pushing against the cross-section of your tubing, you have to physically force that pipe downhole against thousands of pounds of upward thrust. It is literally exactly like trying to shove a garden hose into a fully open fire hydrant.
And check out this fantastic quirk of physics when you're pushing that coiled tubing into a horizontal well. You'd probably think the limit of how far you can push is based on the pipe's tensile strength, right? Like when it might just snap. But it's not. It's actually limited by helical buckling. Because you're pushing all the way from the surface, that long string of pipe acts like wet spaghetti in a tube. It will buckle and spiral into a helix, jamming itself against the walls long before the metal ever actually breaks from tension.
Let's move on to Section 4, freeing stuck pipe with jars.
So what happens when your pipe does get stuck? It is literally every driller's worst nightmare. To solve it, we bring out massive kinetic energy tools known as jars. Fun fact, the energy to free the pipe actually comes from the stored elastic stretch of the drill string itself. The jar is merely the trigger. Now, a mechanical jar has a preset trip load set at the surface. You pull to that exact weight and it fires immediately. Really great for fast, repeatable strikes. But a hydraulic jar, that uses a metered oil time delay, usually about 15 to 30 seconds. And interestingly, because that delay relies on oil viscosity, it completely depends on temperature, taking the longest when the well is cold. This brilliant design gives the operator time to pull as hard as they dare before it fires, delivering an escalating, massive blow.
Sometimes, though, you aren't stuck on the wall. You just have junk in the hole, broken metal or fine debris. For fine junk, you've got two main options. You can use reverse circulation, where upward venturi jets create suction at the tool's nose, or you run a hydrostatic retriever. This thing is so cool. It's a sealed chamber lowered downhole carrying surface atmospheric pressure. When you finally trigger it at the bottom, that massive pressure difference creates a violent one-shot vacuum inrush. It literally sucks the fine or non-magnetic junk right off the bottom of the hole and traps it inside.
But what if you can't just suck the junk out? Well, then you have to destroy it. But you absolutely have to recognize the difference in the physics here. Drilling crushes brittle rock. Milling abrades ductile steel. If you just try to drill a drop tool, you're just going to spin uselessly on top of it. Milling requires entirely different parameters, usually a really light 2,000 to 8,000 pounds of weight on bit and a slow 60 to 100 RPM. That slow, light touch is what lets the tungsten carbide actually shave the steel away.
Finally, let's wrap up with Section 5, overcoming friction and flow.
Let's see how all this builds into the frankly terrifying fluid dynamics of operating in incredibly tight spaces. Welcome to the brutal reality of small bore friction. Just look at this number, 30 times. In small bore tubing, like macaroni strings, friction loss rises roughly with the inverse fifth power of the diameter. What does that actually mean for us? It means if you simply halve the diameter of the bore you're pumping through, your friction doesn't just double, it multiplies by almost 30 times. It's an inescapable law of physics that will absolutely blow out your surface pumps if you don't calculate for it ahead of time. Which naturally brings us to our critical operations checklist. First, we intentionally use that small bore friction to our advantage in depleting gas wells by running what's called a velocity string. The smaller bore speeds up the gas velocity, which actively lifts choking liquids right out of the well. Second, always remember that coiled tubing fatigue is tracked per foot. Every single bend off the spool counts against its structural life, and exhausted sections must be physically cut out of the string once they hit their limit. And lastly, when managing flow, never ever line up your valves just by looking at how the handle is pointed. You must physically verify a valve by function. A handle that got put back on backwards has caused way more disasters than I even want to think about. And just like that, you are fully armed with the physics of the deep. You know how to track invisible fluids using electrical eddy currents, how to perfectly seal against rough rock, how to safely push past thousands of pounds of live pressure, and how to weaponize friction to keep a well alive. You've got the tools, you know the math. So my question to you is, which extreme physical force are you going to challenge next? Keep learning, keep pushing, and I'll see you in the next explainer.